Welcome to this FMSP online revision video for the MEI Differential Equations module, otherwise known as the DE module. This video is going to cover the techniques for first order differential equations, some of which are familiar from other modules in fact. My name's Ben Sparks. Let's have a look at what the MEI specification says about first order differential equations, and you should be seeing some familiar words on the screen. Let me point out what I mean. The first thing it says, you need to be able to find general and particular solutions of a first order differential equation with separable variables. I'm slowing my voice down there because that should be familiar. That's in fact straight out of the C4 content in the MEI C4 module. I am going to mention a couple of skills like that, but I'm not going to focus on that because it should be familiar to you already. What it then carries on to say is this a new stuff, is you need to in general be able to solve first order linear differential equations, whatever that means. In the first case, you need to be able to solve the ones that have constant coefficients. There are in fact a couple of ways to do that, one method of which is much more familiar to you probably from when you've worked on second order differential equations, but you can use them for first order as well, and we'll look at that in a moment. And the rest of this bit is mentioning something called the integrating factor. So we're going to spend most of our time talking about that. In fact, integrating factor methods can solve any first order linear differential equation. It doesn't have to have constant coefficients to use it. I say it can solve it, you can at least get started. Sometimes the integration is difficult, but the process of getting to a solution is at least well defined. So first thing you need to be able to do is recognize when this is appropriate and rearrange equations to get there. So rearrange equations to make it look into a standard form. That's one version of the standard form. I'll talk more about that in a bit. And the rest of these points here just say you need to be able to find an integrating factor, whatever that is, understand why it's useful, i.e. why it's important to learn about and why it's significant, and then you need to be able to use those things to solve an equation, a differential equation in this case. So we're going to look at some examples for this sort of thing, and then look at another method which works on constant coefficients versions. Quick summary of the questions they could ask then. They could ask about direct integration, which is an obvious way of saying just integrate the thing. For example, if you just have a function of x on the right hand side, let's say x squared, dy by dx equals x squared, you can just integrate to get y equals x cubed over 3 plus c. Please don't forget constants of integration. You will fail your differential equations module if you forget constants of integration. They are crazily important. In C4 and C3 and C2 you could get away with just losing a mark maybe if you've got the plus C. No longer. They're really, really important and you'll see why. But I hope the idea of direct integration is not unfamiliar, otherwise you're probably doing the wrong course. The other thing which should be familiar, but maybe less assumptive, less assumed that everyone knows, is to separate the variables. Now you can do that on a differential equation that looks like this. Notice there are two functions, f of x, and multiplied by that is g of y. If you can separate the functions of x and the functions of y, so there's no x's or y's sort of contaminating each other, if you can separate them by multiplying or dividing, then you can use the method of separating the variables. For example, dy by dx equals xy. I can separate the x and y bits by dividing through by y. I get 1 over y dy by dx equals x. And notice I tried to get the y's on the left-hand side with the derivative. Obviously, if they're using other letters, you just have to keep track of which letter is which. They quite often use x's and t's. That's some sort of mechanics application with time and displacement. However it is, you'd proceed by integrating. Neat things happen, which I'm not going to go into here, but log of mod y, you end up on the left, and you'd get x squared over 2 on the right plus c. You won't forget the plus c, will you? No. Good. You can't carry on, you can't get c unless you have more information. Same with the previous question. You need a boundary condition or an initial condition to find out a particular solution which nails down what this value for c is. I'm going to assume this is okay. If it's not, go and revise your C4 stuff. What we're going to focus on is the two other methods, the first of which is the integrating factor method, which works on differential equations that look like this. These are linear differential equations. They are linear because there is no square or power of a half on the y term or its derivatives. If there was, this would not be linear. And notice that the separating the variables thing may end up in a non-linear situation. This g of y could have a different power of y, so we could have y to the half over here. It wouldn't be solved the same way, but it would be a non-linear differential equation, but you could still separate the variables. That's not always true. Non-linear ones are generally harder, and the integrating factor method only works if you have a linear setup. But these functions f of x and g of x could be simple, could be complicated. If g was 0, for example, the right-hand side would disappear and you could use a separating the variables method on it. I'll talk more about that in a bit. The other method is what they call the auxiliary equation method, which can be used on differential equations that look like this. Kind of similar to the one before. Notice this is a linear differential equation still, But instead of f of x times y, I have a times y. This is a constant. If it is not a constant, then this method is not going to be one you're going to use. They actually call this having constant coefficients. So that's the sort of phrase that you might hear when talking about that. I'll give an example of that one later on. So this page is just a reminder without my scribble on of the sort of things that turn up in first order differential equations. Let's look at an example of the integrating factors. So the general idea is if you have an equation in this format over here, then you can solve it by finding this magical multiplier. That's not a technical term, by the way, but they call it the integrating factor. If you can find this thing, you multiply everything by it, it makes life easier. Let me just comment on the standard form, because you may have seen it written slightly differently. If you've seen dy by dx plus py equals q, which is actually written in the specification earlier, that may be more familiar, but please remember that p and q are functions. So I thought I'd write it in a different way, because we're more used to seeing f and g as functions. P and q are functions of x. They might be constants, 1, 3, pi. They might not be, though. And so they often drop the x's at the end here because they're lazy, and we're all lazy and don't like writing them, but they are there. These are functions. So I thought I'd write it in a different way just to emphasize that. The integrating factor is defined to be this little funky looking thing here, e to the integral of f of x dx. In the other notation, they quite often call this r, because that's the next letter after p and q, e to the integral of p dx. That might be familiar. That's in the specification as well. It turns out that this function, when you found the e to the integral of this thing, is a magical multiplier, which when you multiply everything by it, things get better. And I'll show you why they get better. It's important that you know why it works, because they may ask you about it. But once you have done that, you can claim straight away, if you want to, that the integrating factor here times y is the same as the integral of the integrating factor times g. And notice this g comes in here, and the f comes into play because it's part of the integrating factor because of that thing. You may have seen this written as r times y equals integral of r times q. And maybe that's familiar. So you can quote that, but let's look at an example to see why this works. On the left here then we have a differential equation. It is first order, it is linear because there are no crazy powers on the y or its derivatives. It does not have constant coefficients because of this x thing here, but it's easy to see if you compare it with the standard version that f of x in fact is x. The function is just x, and so is g. They don't have to be the same. In this example they are, but they might be complicated, they might be simple. Let's do the honours on this. We're going to find the magical multiplier, otherwise known as the integrating factor. Remember that's defined to be e to the power of whatever the function is in front of y, and that in this case is x. E to the power of the integral of that thing. So if I do that integration, I'll get x squared over 2, and I will get a plus c because you always get a constant of integration when you do an integration. You may be familiar with being able to ignore that. I want to just show you why. I hope it's okay if I immediately write this as e to the x squared over 2 times e to the c. You'll see that that e to the c business is just a constant, so we could write it as a e to the x squared over 2. This is a really common thing when you're dealing with exponentials. And the point of this magical multiplier is you're about to magically multiply everything by it. I'm going to do that now, which is slightly long-winded, but it's important that you see this once. So I'm just writing out the differential equation again with a to the x squared over 2 in front of everything. And you're probably already thinking, well, it's just going to be obvious what's going to happen. Things are going to cancel. And they are, but we don't want to cancel everything, which for reasons which will become apparent. But in particular, we could cancel the a. This a thing, dividing through by it, as long as it's not 0, which, by the way, we're assuming it's not 0, because if it was, this magical multiplier would be 0, and basically I've just made 0 on both sides of the equation, which is true, but unhelpful. Assuming it's not 0, I can divide through by it, and realise that that a doesn't matter. I could obviously also divide through by e to the x squared over 2, but I'm not going to, because that's helpful. But the first thing to realise is that you don't need, for once in your life, you don't need the plus c in this integration, because whatever it is, it will cancel out anyway, so I'm just going to keep this simple by rubbing that all out. It's the only time you're going to get away with dropping a constant of integration. Okay, the reason this is helpful is because the left-hand side is now quite neat. It is exactly this. Well, not exactly that if I put brackets around it and write d by dx of that thing. If you use the product rule to differentiate that thing in the brackets there, you will realise it becomes out exactly to be the left-hand side, as long as you remember that differentiating y with respect to x gives you dy by dx. That's really useful because there's now only one differentiation happened that's relatively easy to undo. The right-hand side is, of course, exactly the same as it was, which at the moment is whatever it was to start with multiplied by the magical multiplier, otherwise known as the integrating factor. So this is great because we can now integrate everything and we'll get e to the x squared over 2 times y, which is just undoing the differentiation on the left, and on the right-hand side we'll get the integral of x times e to the x squared over 2, just changing the order that's written in. So it may now still be hard. We've done the integrating factor bit. We've still got to integrate the right-hand side. In this case, though, it's relatively easy. I'm going to go up here to do that. The left-hand side is still as it was. The right-hand side, in fact, integrates to become e to the x squared over 2. And if you don't believe me, try differentiating that, and you'll realise the chain rule brings an x out the front, which is exactly what we need down here. There is, of course, a plus c. Please don't forget it, because you'll see how crucial it is in a moment. Once I've got this far, I could divide through by e to the x squared over 2. I can do that because that's not 0. Please always check. And I'll get 1 here, plus c e to the minus x squared over 2. And you can see that without the c there, the answer would have been just 1, which, by the way, does solve the equation, but it's not the answer we're after. It's not the general solution. And we can't go any further unless we have more information. We can't find out what c is unless we have some initial conditions to find out what it is. But that's it. That's our general solution for the this first order differential equation using the integrating factor method. These next slides is the same problem just written out in sort of typed stuff. If you don't like my handwriting, this is it typed. It's exactly the same as we've just done. You can pause it and have a look at that if you want. Finishing off with the same solution and pointing out that if you want to carry on, find out what C is, you need more information. So let's look at the other method that we mentioned at the beginning, which is the idea of creating an auxiliary equation and using a complementary function plus particular integral method. There is a lot of vocab in this module, you may have noticed, and it's important that you get used to what it all means. I'll try and summarize bits of it here. You probably will recognize this method from using it on second order equations, and sometimes people just don't realize you can use it on first order, but there's an exam question which asks you to do it, so we'll look at that later on. Let's look at the example here. You could solve this differential equation here using an integrating factor method. You couldn't separate the variables because these y and the x functions are not just joined together by multiplication or division. You could use integrating factor though. We're not going to though. The idea is that for the complementary function method, auxiliary equation, is that you guess the solution is going to be something like e to the power something. And you can see from the previous example that bits of it were. There was an e to the power something in there with some other bits around. Go and look at the method for the second order stuff to see why this is fine. But this exponential function does turn up in differential equations all over the place. And if you do guess that that's the solution, the first thing you try and do is solve the homogeneous case for this, which, by the way, is a posh way of saying the same equation equal to 0. So what we're actually going to do first is solve dy by dx plus 3y. Notice all the y bits are on the left-hand side equal to 0, and that's called the homogeneous version, or homogeneous case. We're going to do that first because you can use that to build the solution to the non-homogeneous or the inhomogeneous case, which is like what we've got here, where it's not 0 on the right-hand side. And then, again, this vocab should be familiar from second order stuff, and go and look at the videos on the second order if you want to remind yourself. If you assume the solution looks like this, then differentiating it will give you y dashed equals lambda e to the lambda x. Putting them into the equation, the homogeneous equation, you'll get lambda e to the lambda x plus, in this case, 3 e to the lambda x must equal 0. Since it's equal to 0, I could divide through everything by e to the lambda x and it'll just disappear. That's fine because it's not 0. The e to the lambda x is not 0. And we're left with lambda plus 3 equals 0. So therefore lambda must be minus 3. And looking back at our original setup here, that means that the solution to the homogeneous case would be some constant, which I'm going to call a, times e to the minus 3x. So that's what they call the complementary function, which is a posh way of saying the solution to the homogeneous case for any differential equation. But our differential equation is not homogeneous. It's got a right-hand side which is not 0, and all we need to do is find a particular function which will give us the right-hand side, because when we add it on to the complementary function will arrange that when we put it into this thing it will be 0, and then the other bit we add on can arrange to get us this 12x that we need. So let's try this. This is called the particular integral, quite often abbreviated to PI. And the way you do it is to have a trial solution. And again, I hope this is familiar from second order work, and it's much easier with a first order differential equation. In this case, we're going to try a function for y that looks roughly like our right hand side, which is a linear function, 12x. So I'm going to write down a linear function. I'm going to use Greek letters alpha x plus beta. I do need both of them. A linear function can have an x term here and a constant term. If I differentiate this, y dashed is just alpha. And if I put those things into the differential equation, I will get alpha from the y dashed plus 3 times y, which is 3 alpha x plus 3 beta. And for it to work, I need it to equal 12x. And this is nice and easy. I can compare the left and right hand sides. I can see the amount of x's on the left is 3 alpha, the amount of x's on the right is 12. This is a process called comparing coefficients, but I can immediately say that 3 alpha must be 12, i.e. alpha is 4. And I can also say the constants on the left are alpha plus 3 beta, and there's nothing on the right. So alpha plus 3 beta is 0. I now know that 4 is alpha, so I can finish the job here and realize that beta is minus 4 over 3. So I now know that if I put alpha and beta as 4 and minus 4 over 3 into that, I will have a particular solution or a particular integral, and the solution to the whole equation is the combination of the complementary function with the particular integral. In this case it is precisely this. Keep the constant in there, a e to the minus 3x plus, in this case, 4x, that's my alpha x, minus 4/3. And that is my general solution. There's so many two-letter acronyms. We've got auxiliary equation, by the way, that's this thing. This is the auxiliary equation. We've got the complementary function, we've got the particular integral, and we've got the general solution, which is quite often called GS. But that's it. You can solve first-order linear differential equations using this complementary function plus particular integral thing, and they sometimes actually make it very easy to do it that way in the exam, and we'll see an example of that in a bit. Okay, let's look at some exam questions which use these. So I'm taking some questions from the 2010 January paper, and I'm also going to look at the June 2010 paper here. This is question 2 part A. 2 part B handles something slightly different. Go and look it up if you care about it. But let's look at how to answer this question using what we've just done. It is clearly a first order linear differential equation. First order linear, no powers of craziness on y and its derivatives. It does not look like the variables are separable at first glance. In fact, they are, but it also looks like the standard formula for an integrating factor approach, and both methods will work on this. In fact, you can't use the auxiliary equation, complementary function, particular integral stuff because it's not got constant coefficients because of this tan x, but the other two methods will work. So let's look at both of them. Quick glance down at the question though. They've given us a condition on x that might be important. We've got to find a general solution, and then it looks like a particular solution. The only information they give us is that it goes to the origin, but they do want us to draw it, and that's quite a common thing. Let's focus on part 1 to start with though. I'm just going to pause and check this is good. So part 1 I'm going to do in 2 ways. Let's do an integrating factor method first of all. Let's call that IF. So first things first, I need to recognize what the integrating factor is. In this case, the magic multiplier or integrating factor is going to have to be e to the power of the integral of minus tan x. That looks a little bit more daunting than normal, but I do need to integrate tan x, and actually I hope it's something you recognize, and if you don't, it's worth learning that the integral of tan x is log sec x. But first of all I'm going to put the minus outside the integration because that will make life a little easier. So now I can do e to the power of minus log of sec x. If you're not sure what sec is, go and look it up before you go any further, because you do need to get used to that. It's actually 1 over cos, but go and get used to it. It's going to be an important bit to recognise in this. I don't need to worry about the plus c for reasons we discussed earlier, and there's also something neat. I can put this minus sign up as part of the logarithm, and then it would be sec to the power of minus 1, which would be 1 over sec, which is exactly the same as cos. So I can rewrite this as log of cos x. Pause there and reflect if you're not sure what just happened, but this is good because I've got e to the power of logarithm something, so this is just cos x. The integrating factor is cos x. Multiplying through by cos x would give us something nice, and I'm going to shortcut jump to the final solution, which means that r times y, so cos x times y, is the same as the integral of r times the right hand side, which is cos x times tan x. And I'm already thinking, oh, that's nice, because I know what cos x times tan x is. Tan x is sine over cos, so multiplying by cos will just give me sine x. And I'm relieved because I can integrate that. And I think I'm almost done. I better do this though. Let's do cos x y equals, the integral of sine x is in fact minus cos x plus c. Finally, divide by cos x everywhere. I should check whether that's going to be 0. But they've limited my x values here, so I think we're okay. We're never going to get a 0 out of cos x. And this is going to become minus 1 plus 1 over, or c over cos x, which is going to be c sec x. That is my general solution. Now, I don't know whether you liked that method. It did need some careful integration of tan, and maybe that would have scared you. So if you did spot it, you can do this by separating the variables. Let's do that as well. I'm going to rewrite this as dy by dx equals tan x plus y tan x, because then it's obvious you can factorize. This is quite often a way to spot separating the variables approach is okay by factorizing. And you can see that I've factorized it into an x function and a y function. So if I was going to do this by separating the variables, I'd write 1 over plus y, that's the y function, dy by dx, equals tan x. And I still have to integrate tan x, so you can't get away from this. But the left-hand side I've got to integrate, and that's going to become log of 1 plus y. And on the right-hand side I've got to integrate tan x, which we now know is log sec x. Plus c, don't forget it. Now exponentiating gives me a 1 plus y on the left, and I'll get a e to the log sec x. Remember that standard trick, if you've got a plus c and you exponentiate, it's going to become a multiplying constant. The e to the log bit is going to cancel out, giving me just 1 plus y equals a sec x. And finally, I'm going to get y equals minus 1 plus a sec x. And you can see that doing this is giving me exactly the same answer. All that's different is I've written a c for the constant and an a here, and that's just by habit of the way I've gone through it. But it has given us the same general solution. So that's part 1 done. Pause it if you want to go and reflect on that. Either way should get you full marks. In the examiner's comments they said that the people who used the integrating factor got confused, which I think is a shame, because I think it's quite a neat method, and the people who used the separating the variables, if they spotted it, did rather better. But there's no reason why you can't get full marks from either way of doing that. What they ask us to do next is find the equation of the solution curve, the particular solution curve that passes through the origin. That is a clever way of saying that when x is 0, y is 0, and you've got to sketch it. So it's taking the words and turning it into a condition, but we know when x is 0, y is 0, otherwise it wouldn't be going through the origin. So let me just remind you what the answer was. It was minus 1 plus a sec x. That's our general solution. I could write it as a sec x minus 1. And I now know that when y is 0, x is 0. So you need to figure out what sec of 0 is. The best way to do that, I think, is to always have in mind what sec is. It is 1 over cos, and cos looks like this as a graph. So 1 over cos, and actually I should realise that I'm only going between this point there and this point there. 1 over cos, therefore, what would that look like? Well, it's going to look like 1 over 1 at that point, and when you get towards 0 down here, it's going to be 1 over 0, which is infinity or something horrible. So these two things become asymptotes, and that's what the sec graph looks like. It heads up to an infinite asymptote at that point. But it's obvious that when you put 0 in there, we're going to get 1, so we're going to get 0 equals a minus 1, so a is just 1. And my particular solution is therefore just sec x minus 1, which we now need to sketch. But we've done a little thinking about the sketch in order to work out the values of sec, so actually let's just sketch this properly. First of all, they've told me that mod x is between mod x is less than a half, which means x is between plus a half pi and minus a half pi. So let's mark them on. And I can't go either side of that, but that's good because that's where cos is 0, therefore sec is infinite. So these are asymptotes at these points. But I don't need to go beyond those, which is nice. It's the same as this graph, which I was sketching for sec, but it's had 1 taken away from it, and that's not a surprise because it's got to go through the origin. It told us that, so we can now draw this going up like this. And that sort of sketch, as long as you've marked in the important points, I think you need to mark in the asymptotes here, But if you've done that, you're going to get 4 marks for that. And that is the end of January 2010 D question 2A. Let's have a look at another exam question. This is from the June 2010 paper this time. Again, it's question 2. There are only ever 4 questions on a DE paper, and almost certainly one of them is going to involve a bunch of first-order differential equations. So in reviewing this stuff, you're probably reviewing a quarter of the course, or a quarter of the exam. This question is going to take us a little bit longer, because I'm not going to skip part B this time. All of this stuff is relevant for us. Let's start with part A, part 1. It just says find the general solution of this thing. It's first order, it's linear, it looks like we can't separate the variables. The other confusion thing is that it's not dy by dx, it's dy by dt, and maybe that scares you, but you need to get used to the fact that they will change the variables from time to time. Let us proceed by suspecting that we're going to have to use either an integrating factor or a constant coefficient method. We could use either. I am going to use an integrating factor method because I think it's neat. So let's find the integrating factor. It's going to be actually quite easy. E to the power of the integral of whatever the function is in front of the y. In this case it is 2. And I'm using t's instead of x's, which means the integrating factor here is e to the 2x. Of course, that was rather stupid of me. I just mentioned I'm using t's, so I'm not talking about x's, I'm talking about t's. That is my integrating factor. Let's do it properly here. I'm going to multiply everything through by e to the 2t, dy by dt. You don't always have to write this, but it's just reminding you how this is working. And on the right hand side I get 2e, no I don't, e to the 2t. Times e to the minus 2t. Something rather neat has happened. So on the left, it always works like this. You're always going to get the integrating factor times y differentiated. And on the right, you'll get whatever's left. In this case, it's just 1. Integrating this is actually rather easy. E to the 2t y equals the integral of 1, which I'm going to jump straight in with t plus c. And we've got a simple situation now. To get y equals, I'm going to get y equals t e to the minus 2t plus c e to the minus 2t. And maybe you just write that as e to the minus 2t brackets t plus c. Either way is fine. But that is it. That's apparently 6 marks. If you use the integrating factor method, I don't think it's too hard at all. You may want to pause and try using a auxiliary equation or complementary function way of doing that to see if you prefer it. But that, believe it or not, is 6 marks. It's important to realise that you can't find out what C is because we have no more information yet. But we don't need to because it hasn't asked us to. The next bit asks us to find the solution of another differential equation. And the reason you should be suspicious is that this is in the same question as what you've just done, and it looks quite similar. Let's just summarise what it's asking. The dz by dt plus 2z equals y, where y is the solution we just found in part 1. So I could immediately replace y with that to see what happens. But we've also got conditions. So it's possible that we actually don't need to find a general solution, and it in fact is telling us we don't need just a general solution, we need a particular solution. If they omit the word general, they do mean a particular solution. But it should be obvious because there are conditions, there's more information. Let's play with this briefly. The dz by dt business plus 2z is exactly what we had on the left hand side. It's just with y replaced by z. So actually I can immediately claim that the same thing is going to happen because the integrating factor business is exactly the same. It doesn't depend on the right hand side until we start integrating the thing. So I think the integrating factor for this one is going to be exactly as it was before. It's going to be e to the 2t. And immediately I can write down e to the 2t z equals the integral of the right hand side, which in this case I'm just going to write as y, also times e to the 2t, the integrating factor. If I then replace the y with the solution we had before, we actually get the integral of e to the minus 2t brackets t plus c times e to the 2t. And you see nice things happen, these two things cancel out. So finishing the job here, e to the 2t z is the same as the integral of t plus c. And I'm doing dt, I've been forgetting to write that, but never mind. Finally, e to the 2t z is the same as t squared over 2 plus ct plus, I'm going to use a new constant of integration, I'm going to use d. And let's tidy this up to get z equals. So z equals e to the minus 2t, I'm going to put it in brackets, t squared over 2 plus ct plus d. And that's as far as we can go without using the conditions. So let's have a look at what else they've told us. I've used the fact that y is the general solution to get this sorted, and I used the sort of reusing the technique from part 1. I now need to put the conditions in that z is 1 and dz by dt is 0 when t is 0. In order to use that, I might need to use what dz by dt is, but bearing in mind I might be able to get it out of this as well, because the original equation was relatively simple. First off though, z is 1 when t is 0, so I can put that in here. T is 0 is going to make that thing 1, the e to the minus 2t, and t is 0 is going to make that first term disappear and the second term disappear, and I'm just left with d. So lo and behold, d is 1. In order to find out what c is, I need to use the second bit of condition, but I'm just going to point out that from the original equation, this is just a neat little trick, nothing wrong with spotting this, is y minus 2z. That's what dz by dt is, and I know that y is e to the minus 2t brackets t plus c minus 2z, and I also know what z is. So at t equals 0, dz by dt is 0, so 0 equals e to the minus 2t, which is 1, t is 0, c is left there, and 2z is going to be 2 times 1, so that's just minus 2. So I now know that c is 2, and I'm done, because I can now write down the particular solution, z equals e to the minus 2t brackets t squared over 2 plus 2t plus d, which is 1. And that is my particular solution, and again, believe it or not, although I've done it quickly and you may need to pause to reflect on it all, that is worth 7 marks, mainly for reusing the stuff we did in part 1. It might be worth mentioning that if you don't spot this trick that I used with the original equation, you could have always done it by grabbing this z definition we had here and differentiating it to get dz dt. You can always differentiate your solution, but it's a bit horrendous because you're going to have to use the product rule because we've got an e to the minus 2t times that thing. So it's actually in this case much quicker to spot that we've got a definition for dz dt in terms of stuff that we already know. Quite often though, you'll find yourself differentiating the solution you get in order to use a condition on the derivative of the solution. Let us continue by looking at part B of the June 2010 question 2. It is definitely part B rather than another sort of part 4 carrying on or part 3 carrying on, so it's probably going to be different, although notice that it does look quite similar to the one we just looked at. The left hand side is the same, but this time it's telling us how to solve it. It wants you to use a complementary function and particular integral approach, even though we could probably solve this using some other methods. So let's do what we're told. We've got to find the complementary function. Remember, that's the solution to the homogeneous case, so the solution to dx dt plus 2x equals 0, and we can do that by guessing that x is something to do with e to the lambda t. In general, you just jump in by rewriting the equation as lambda plus, in this case, 2. If that looks way too simple, you're normally doing this with second order and you have a sort of lambda squared floating around, and hopefully that sounds familiar. This is the auxiliary equation. In this case, lambda must be minus 2. So what I've now realised is my complementary function, which I would write as CF, is x equals some constant I'm going to call a, e to the minus 2t. That is the complementary function, and it's remarkably easy to get to. Let's look at the particular integral, and to do this we need to try a solution. The right hand side is a trig function, so the obvious thing to do is try a solution which is made of trig functions. All we need is to find a solution that fits this. We can add it onto the complementary function and we have a general solution. But in general, just like with second order, you need to try both trig functions in order to get one of them. So I'm going to use Greek letters. I quite often use Greek letters in this bit. I'm just used to that. I also always start with the same trig function. I always start with cos, just because there's a lot of identities of trig that always start with cos, so I just get used to always starting with cosine. It's good to get into habits so that you get familiar about what's coming first every time. That is my trial solution. It is some linear combination of trig functions. I'm only going to have to differentiate once. I'm going to write it as x dot because that's shorthand for dx dt, and this always happens. I'm going to get minus alpha sine t by differentiating that, plus beta cos t. That's dx dt. Putting those two things into the equation gives me, I'm just going to shortcut by writing sines as s's and coses as c's. I'm going to get minus alpha s plus beta c. I'm also going to get plus 2 lots of the x1, which is alpha c plus 2 beta s. And altogether that's got to equal sine t, which in my shorthand is going to be s. I think this shorthand is useful. It's particularly useful when you're doing second order stuff and you've got huge bits of algebra to keep track of. As long as you don't forget if there's a coefficient in front of a t, maybe there's a 3t in there, this notation I'm just using would not make that obvious, and you need to remember it. In this case, though, comparing left-hand side and right-hand side, the number of s's on the left is minus alpha plus 2 beta. So that's got to equal 1s to get this s sorted. And the number of cosines, well, it's got to be 0, so beta, lots of cosine, plus 2 alpha is equal to 0. When you do these sort of things, there's always a nice sort of symmetry in the way of the structure of these two equations you get out. So watch out for that. I've got a minus alpha plus 2 beta, and then I've got a beta plus 2 alpha. There's a sort of usually a sign reversal somewhere, and the order is reversed. Solving this is pretty easy. Beta must be the same as minus 2 alpha. So I can replace beta with minus 2 alpha, which means this one is going to give me minus alpha minus 4 alpha equals 1. Altogether, I think that means alpha is minus a fifth, and therefore beta is minus 2 times that, which is 2/5. So I've got alpha and beta. My particular integral is therefore relatively easily got by plugging those two into that. I'm not going to write it out separately. I'm just going to finish by writing the general solution, which is the complementary function plus the particular integral. In this case, a e to the minus 2t plus, now let me get my alphas and betas sorted. Actually not a plus, let's go with minus a fifth for the alpha times cos t plus 2/5 sine t. And that is the general solution, and again we've earned 6 marks quite quickly. Again, I'm used to doing this, and by the time you've done lots of practice you'll be used to it, in which case you can also earn these 6 marks very quickly. So what happens next in the rest of the question is quite predictable. It looks like they're going to give us some conditions, and then they quite often, this has happened again, they're asking us about large positive values of t. So what happens to this behaviour of the solution as time goes on? They quite often ask things like this. Let's look at part 2. I've copied the general solution from part 1 here, so we've got that to reference. This time all they're telling us is that dx dt is 0 when t is 0. I've just realised I've written a rather annoying thing, and maybe you spotted it earlier, and I've only just realised that I shouldn't be writing y here at all. This is x. In this case that should be x. You can see how easy it is to make a notational mistake like this when we're so used to using y's and x's. So stay on your toes about that and try and dodge those things. Get used to it early on in the question. Let's sort it out though. It looks like in order to sort this out I need to know what dx dt is, and this time I'm going to do it by differentiating the solution. So x dot from this is going to be minus 2a e to the minus 2t minus a fifth of differential of cos. I know cos differentiates to sine, so that's going to become plus. So cos differentiates to minus sine, it's going to become plus a fifth sine t. Differentiating sine goes to cos, so I'm going to get 2/5 of cos t. That is x dot. They're telling me it's 0 when t is 0, so if I put 0 there and put t's in for 0, I'm going to get minus 2a. The sine term disappears because sine of 0 is 0, and cos of 0 is 1, so I'm going to get plus 2/5. And sorting this out gives me that a equals exactly 1/5. And we've got a nice recurring theme of fifths coming out here. This is only 3 marks, so it's no surprise that it's over quite quickly. X now, I know, is equal to a fifth e to the minus 2t minus a fifth cos t plus 2/5 sine t, and it's almost always going to be easier to write this factorised because there's a fifth everywhere, so it's e to the minus 2t minus cos t plus 2 sine t there, and that would be a particular solution that satisfies those conditions. That's the part 2 done. So let's finish the job. 2 marks to go for part 3. I've copied the solution out from part 2 there, and it's asking us to find approximate bounds between which x varies for large positive values of t. So 2 warning words here. We've got approximate, so we're not seeking exact answers, and we've got this large positive values of t. That's the other word that's triggering. Like, we're expecting t to run on for a while, and you'd quite often do that by writing it as t goes to infinity. Positive infinity in this case. It becomes obvious what happens to the solution if you recognise what happens to exponential functions. In particular, e to the minus 2t, or e to the minus anything to do with t, is going to head towards 0 as t gets really large. Which means that x is going to head towards and head towards is maybe a less technical word, but tends towards whatever it was without that e to the minus 2t thing. So it's going to be a fifth of minus cos t plus 2 sine t. And so first things they might ask you in a different sort of question to describe what happens for large positive values of t. And because this function now only has trigonometric bits, it is oscillating. And you must know from sort of C3 and C4 trigonometry that you can always rewrite sums of trig functions as another trig function. So in particular, let's talk about this one. Let's talk about a fifth of, I'm going to just write it as 2 sine t minus cos t to get the minus signs in a nice way. I suspect this could be written in some other format as r times, and let's do a sine of t minus some angle, which I'm going to call phi. I could call it anything. But you'll remember from double angle or addition formulae that we could always rewrite this as sine t cos phi minus, because of the minus sign. And you can see I've chosen the minus to match this thing. Cos t sine phi. This is using the addition formulae for trigonometry. But I didn't actually need to do this, because if you're familiar with it, you always remember that you end up comparing the right and left sides. So let me just expand this out. And if you look from this, I can deduce that the r cos phi, so that bit, must be the same as the coefficient of sine t, which in this case is 2/5. So 2/5 must be r cos phi, and similar argument, I've got minus 1/5 must be r sine phi from looking at that bit. And actually, I don't really care what this phi business is, because all that's going to do is shift a trig function. What I do care about, because they're asking about the bounds, is how big this trig function gets. The reason this is helpful is that we know what sine does. It goes between 1 and minus 1. So if I find out what this r is, I've got the bounds which this function goes between. And I can do that by squaring and adding these two things together. It always happens like this. So if you square and add these things, we're going to get r squared is the same as, in fact, the 5 is just going to come out the front. Let's do it properly though. It's going to be 4 over 25 plus 1 over 25. Adding that together, we get 5 over 25. So finishing off, just running out of room, r is root 5 over 5. And so to actually answer the question carefully, and bearing in mind, they might be picky for the last marks of this question, the bounds, x goes between root 5 over 5 and x is always greater than minus root 5 over 5, because sine could take a minus 1. So that would be much better to write in the format like this. If I'd actually planned ahead, I would write it like that, or even better, mod x roughly changes between root 5 over 5 and minus root 5 over 5. I could do that with mod x just being less than root 5 over 5. So that answer, I think, would get you the final 2 marks. They're probably harder marks than the other ones to get, and they're harking back to how to recognise what trig functions do when you add them together. If you can turn it into one trig function, you know how high and low it's going to go. And if you cared, you could figure out how far it's been shifted from a normal sine graph. And they're not asking for that this time, though. It's a good thing to be able to recognise when a solution is oscillating, though, and when you see trig functions, you know it's oscillating, and they will quite often ask you to describe that. Okay. I'm going to stop there for this video. We have done quite a lot of ground. We've covered all the first order stuff that's not already in other modules, and we've done a few exam questions. There are going to be other videos on other topics in the DE series, and also some other videos on other exam questions from the years I've been looking at. Hope you found it useful. My name's Ben Sparks. See you on another video. It might be worth mentioning that if you don't spot this trick that I used with the original equation, you could have always done it by grabbing this z definition we had here and differentiating it to get dz dt. You can always differentiate your solution. But it's a bit horrendous because you're going to have to use the product rule because we've got an e to the minus 2t times that thing. So it's actually, in this case, much quicker to spot that we've got a definition for dz dt in terms of stuff that we already know. Quite often, though, you'll find yourself differentiating the solution you get in order to use a condition on the derivative of the solution.